Okay, here we go. So yesterday we dealt with biscuits that were cuboids. So the surface, the cross-sectional area they were squares. But this time, our cookies are in the shape of cylinders. So because they are cylinders, and they want them to be packed into boxes that look like this, so we can expect some free space, some wasted space at the corners of all of them. Okay, but that's not the important thing about this question. They want us to find out the total surface area required for each of these containers. So to find out the total surface area for a cuboid, which is what all these three are, we need the length, the breadth, and the height. And we've actually found out, some of them already. Right, so in box A, we saw that the length was 6 cm, the height over here also 6 cm, because that is the diameter of the cookie. Now there are 20 rows of cookies, so we need the final distance over here. This will give us 20 multiplied by the thickness of each cookie is given to be 3 cm. Okay, so 20 times 3, we get 60 cm. So here we have the three required dimensions. Do you have this in your diagram? Okay, you should have this. Let's do the next one. Here in box B, the horizontal distance will be 12 cm. Vertical distance 6 cm. And this distance over here will be 10 multiplied by 3. And we get 30 cm. So we see that because we are stacking them also side by side, the length of the box becomes shorter also. It is half. Now in the final case, box C, distance 12 cm here, vertical also 12 cm, and the thickness, we've got 5 cookies, so 5 times 3, we get 15 cm. So these are the dimensions you need to be able to come up with yourself before we can talk about calculating the total surface area. So find the cost of manufacturing of each box, given that, okay, 20 cents per 0.01 square meters. So we have to first find out total surface area for each of them. Okay, I'll be putting my working at the side. You can do it at any free space that you have. So total area for A. Remember, the total surface area is made out of the two cross-sectional area, the highlighted portions. There is one at the front and one at the back. So let's put that down first. For the first cross-sectional area, it is a square given by 6 multiplied by 6. So it is 36, or you can write it down as 6 square. And there are 2 of them, so multiply this by 2. The next, what we need to do is find out the perimeter of the first cross-sectional area. Whatever I've outlined over here in red, we need to find the perimeter, and it is not difficult. It is 6 plus 6 plus 6 plus 6. 6 plus 6 plus 6 plus 6. And because it is so long, a distance of 60 cm, we're going to multiply this perimeter by 60 cm to get the other 4 surface, the other 4 areas, lateral faces areas. So multiply this by 4. Use our calculator to help us. We've got 24 plus 24 times 4. No. 36 times 2 plus 4. Okay, so we get 168 square centimeters. Okay, I give you some time to check whether you have the same surface area as me. You have it? Okay, leave some space over here because later on we are going to convert it to square meters. And I want to do everything at the same time. So total area for B. Total area for B, we use the same approach. 2 times of the same cross-sectional area. This time the cross-sectional area highlighted is a rectangle. It is no longer a square. So the area of this rectangle will be given by 6 multiplied by 12. Or 12 multiplied by 6, they are the same thing. 12 multiplied by 6. And there are 2 of them, one in front and one behind. Multiply this by 2. So right now, I've got the 2 cross-sectional areas. I need to add the perimeter in red color. I just switch it to red. The perimeter is given by 6 plus 12 plus 6 plus 12. So that is the perimeter. Yes? Sorry? Oh, sorry. It should not be. Should not be 4. It should be. What should it be? $60. Thank you for pointing that out. I don't know why I wrote 4. Oh yes, I'm a little. Thank you for giving me that reason. So this is supposed to be multiplied by 60. 60 came from the length over here. So I made a mistake over there. Let me just rewind. 36 times 2 plus 24 times 60. Okay. So this is 1512 square centimeters. Is this correct now? Hey, then you told me you got the same answer.
I never see until.
Okay, now total area for B. So 2 times of the cross-sectional area plus the perimeter, and we multiply by this distance over here, which is 30 cm. Multiply by 30. So calculator again. One, two, two, four? 1344. Sure not? Okay, now total area for the last one. Help me check my work. Okay, so I need the cross-sectional area. That will be 12 times 12. 12 times 12. And we've got 2 of them. One in front, one behind. So multiply by 2. Then I need to add the perimeter. Perimeter of the cross-sectional area is given by 12 times 4. Or you can write 12 plus 12 plus 12 plus 12. We multiply this by the thickness. So there are 5 cookies, 5 rows of cookies. We calculated it as 15 centimeters. So this will give us, okay, hang on, let me calculate it for myself also. 48 times 15. 1008 square centimeters. But they told us that the cost is calculated by per square meter, or rather per 0.01 square meter. Over here. Okay, the units are in square meter, but our units over here are all in square centimeters. So we need to do a conversion. Exactly, divide by 100 squared. To go from cm to meters, we divide by 100. To go from square centimeters to square meters, we divide by 100 square. Okay, so coming back to our calculation, let's do the conversion. One five one two over 100 square, and this gives us 0.1512 square meters. Okay, move the decimal place by four times. 1, 2, 3, 4. Get 0.1512. Alternatively, just use your calculator. So 1224 divided by 100 square. 0.1224 square meters. The last one, divided by 100 square, 0.1008 square meters. So these are the areas for all three containers. And I need to find the cost, because that's what the question wants. Find the cost of manufacturing each box. Okay, continue in the space that you have. We know that 0.01 square meters cost 20 cents. So for box A, the area is 0.1512. 0.1512 square meters will now cost take this value divided by 0.01, then you multiply by 0.1512. So that is the order we are going. This way, then this way. (0.20) divided by 0.01 multiplied by 0.1512. $3.24. Sorry, $3.024. So because we are dealing with money, we have to round it off to 2 decimal place, right? The smallest cent that we have is 1 cent. We cannot go lower than that. So round this off to 2 decimal places. We get 3.02. So this is the cost for A. Now for B, the area is 0.1224. It will now cost, same thing, 0.20 divided by 0.01 multiplied by 0.1224. So the value is 2.448. Because we are dealing with money, we need to leave it to 2 decimal places. 2.45. And the last one, C. 0.1008 square meters. It will now cost, same working, so these are the answers for part A. Okay, once we have this already, try and make sense of the numbers. And what will your answer be for part B? Which design will you choose? You choose C. I will choose C. If they ask you why, the reason is because it is the cheapest. Okay, now the next type of question that we may see. Find the maximum number of small cubes or cuboids that can be packed in a large container. First, do you understand what this question is trying to tell us? So here we have small cubes. The dimension of the cube is 2 by 2 by 2. So imagine a dice, okay, each side 2 centimeters. We're going to pack it into this container. But instead of just dumping everything in, I want to pack them very neatly so that we don't have any extra free space. They wanted the maximum. How many dice do you think you can place them at the sides here? If this is 30 cm long and one dice, or rather one cube, has a length of 2 cm, how many do you think we can have here? How many? 1/5. How do you get 1/5? Okay, so total number equals to 30 divided by 2. So here we have 15. That is horizontally. Horizontally we can put 15 side by side. That will be just nice 30. What about this side? If I were to put them side by side very neatly, how many do you think there will be? Okay, 20 divided by 2, we get 10. That's the number of dice or cubes. But there's one last dimension, right? We can also go upwards. We can stack them upwards. How many would there be? We stack them this way. Each dice, each cube being 2 centimeters. If the total height is 10 centimeters, we can put 10 over 2. We have 5 of them. Okay, based on this, what is the maximum number of cubes? What are we going to do with this 5, 15, and 10 that we have found out? Yeah, let's multiply them all together. Because it shows us that we've got 5 levels of the dice. 2, 3, 4. And then we've got 10 over here. 2, 3, 4, 5, 6, 7, 8, 9, and 10. Then we've got 15 of them. Okay, I'm not drawing to scale, and I'm not counting also. But you get the idea. Same over here. And we multiply these 3 numbers together to find out the total number of cubes inside. So our working is just total number equals to 15 or 5 times 15 times 10. Okay, here we have part B. So as expected, you can't just take the total volume over here divided by this total volume over here, unless you find out whether you can actually fit them all without any empty space. Alright, so now this is a cuboid. The dimensions are different. Early on it was 2 by 2 by 2. Now it is 3 by 2 by 2. How will you want to arrange this such that you can fit the most inside? if we leave it as it is and we put it in this corner, 3 by 2 by 2. Is this a good idea? Is this a good idea? You have to imagine me, it is a real life application problem. Maybe next time you are working in sales, you need to pack stuff. You want to pack as many into a box as possible. Will you pack it this way? What's the problem here? What's the problem if you pack it this way? There'll be 1 cm gap on top. See, if this is 3 cm here, they put another 3. Okay, let me draw it more to scale. 3 cm, 3 cm, 3 cm, right? Then you have a gap of 1 cm over here. Wasted space. So it's not a good idea. So cannot just directly put it in this way. I can rotate this, right? It is just a box. I can put it this way, I can put it this way, I can put it this way. So how will we do it? See, the problem over here is this 3 cm over here. 10 cannot divide by 3 to give me a whole number. What about 20? Can 20 divide by 3 to give me a whole number? Cannot. 20 divided by 3, I get a fraction, decimal. So it doesn't make sense for me to put a 3 cm here. Doesn't make sense. Then what other option do I have? Has to be this 30 cm. Okay, since this is 30, this is also 30 cm. Let me try and arrange them here. 3 cm. So this is my cuboid. If this is 3 cm, then this is 2 cm over here. And this distance also 2 cm. Would that work if I do it this way? Let's check. The height, if this is 2 cm, how many can I fit over here? 5. I can fit 5 because 10 divided by 2 is 5. Okay, I can fit 5. Fit 5. Now over here, how many can I fit? Yeah, 30 over 3 equals to 10. Okay, this 5 came about because of 10 over 2 equals to 5. Then, on this side, I can fit how many? Is it also 5? This distance over here is 20 cm. The dimension of the cuboid is 3 by 2 by 2. We have already used the 3 over here, we have used the 2, the remaining dimension is 2. So we can fit 20 over 2, which is 10. In this configuration, by arranging it this way, there's no extra space. So I can have the maximum. Okay, so here we have maximum number equals to 5 times 10 times 10. 500.